Okay, hi everyone. This talk is about hacking and craft. So I'm a electronic engineer mostly, also a kind of mechanical hacker of things, and I'm currently studying to become a product designer. I'm at the Royal College of Art in London, learning how to make arty shit like this. So when you talk about craft and hacking, people immediately think about 3D printing as the sort of confluence point between the digital world of hacking and printing stuff out into the 3D physical world. But in this talk, I want to focus a little bit more on Lowtech. So just before Christmas, my friend Connie was in Berlin, and she was trying to get this keychain engraved with some mathematical symbols. So it seems like a pretty simple job. You take it to an engraver's, give them an image, and they should engrave it. But unfortunately, all the engravers were set up to either stamp with a set of metal stamps A to Z, and probably in Germany some accents as well, and couldn't handle mathematical symbols. She went to industrial laser engravers. They had no problem engraving any shape possible, any sort of vector format, but they couldn't deal with constructing the artwork in the right file format. So despite the fact that the technology is progressing rapidly in the world of laser cutting and all of that, it was impossible to just engrave a simple keychain. About 200 years ago, if you'd go to any engraver shop on the corner, you would find a guy like this who would engrave it with a hammer and a chisel, and you could have almost any design of your choosing engraved on the spot. So somehow although our technology is advanced, we're also forgetting some existing technologies that were much more powerful in certain ways. So I sort of think that hacking is a form of craft. Hackers and craftspeople have, I think, very much the same mindset. We both focus on the detail in things, and we, I think, both do things for the love of doing a good job. So it might not make sort of economic or sort of timekeeping sense for us to design pieces of software to be extra modular and really extensible and clean and elegant, but we do it for the same. We do it just for its own sort of internal beauty. It doesn't necessarily. It's not really efficient necessarily, but we do it for the love, and that's definitely something that craftspeople do. I think hackers can learn from craftspeople, and craftspeople can learn from hackers, and we can both end up essentially doing the same kinds of things. So the first section is about using hacking tools for better craft. And I want to talk about inkjet printers. I've got a project on at the moment that I've been working on for a few years, reverse engineering inkjet printers to make them much more powerful 3D printers. So thermal inkjet printers work this way. You have an ink reservoir up on the left there, and the ink flows down into a chamber where it's heated rapidly and gets ejected by the force of creating the steam behind the droplet, essentially. There's also this kind, which is a piezoelectric membrane, so you can deflect this little membrane electrically and then pump out a little droplet like that, and that's called DropOnDemand Piezo printing. Now these things are crazy. You can go to MediaMarkt or PC World or whatever and pick up a printer like this for about 40 euros, possibly even cheaper now, and it can deposit 4 picoliter droplets, so tiny droplets, huge degree of precision. Each droplet's only got a diameter of about 19 microns. Your hair is about 50 or 70 microns wide. So it's pretty incredible that we can pick this technology up for such a low cost. But the question is, can we hack this technology to achieve more? This is very much a kind of razors and blades business model where the printer is sold possibly at a loss to get you into a relationship with the manufacturer where you have to buy more and more ink, and the ink cartridges are almost as expensive as the printer. But there's an opportunity, obviously, if we can get to the interface to the printhead and harness this really high-tech printing technology to print arbitrary materials. Maybe if you're into biohacking, you could use it to print DNA arrays for DNA assay. If you're a sort of crafter like me, you might want to print out some wax and use it for casting. So it has lots of applications. So when you take one of these machines apart, you see one of these print heads, which has, in this case, 4 tubes for accepting the red, cyan, magenta, yellow, and black inks. And then on the other side, this is the print plate. And you might possibly not be able to see on this projector, but there's a pair of thin grey lines down the middle. Those are arrays of inkjet printhead nozzles. And there are 90 nozzles in a line on a very, very tight pitch. I think that's about 20 millimeters wide. And in there's 90 black nozzles and then 30, 30, 30 cyan, magenta, and yellow. So very, very high density of nozzles to print rapidly. If you take it apart further, that's what the printhead looks like. And this is what it looks like from the back. You can see the 3 ports for the colors, the 1 port for the black, and this electrical interface here. And on that chip, on that flexible circuit board in the middle, that's our target. That chip has a serial interface to the, sort of a mixed serial and parallel interface to the printer. And internally, it has some multiplexing, which it uses to switch onto the different nozzles. And what we want to do is drive the printhead at a very low level so that we can directly control the nozzles and we have more access over the hardware instead of having just sort of Epson photoglossy mode or economy mode or some bullshit. We just want to be able to directly control the nozzles. So that's the goal. If we go in a little bit closer, we can see this is peeling apart the inside of the printhead, and you can see how the ink is distributed from the input port up to all the little tiny holes. And you can see the amount of refinement and engineering complexity in these printheads is really incredible, and it's accessible for no money. So definitely a good hack platform. So we want to be able to supply arbitrary materials to the printhead rather than just use the cartridges that we're supplied. So I made this little reservoir on the lathe and mounted the printhead on the bottom. So here we can see the projector's doing some interesting stuff. Cool. So I wanted to print liquid wax on my platform because that opens up potentially 3D printing. If you can print tiny droplets of a thermoset material, you can make quite complicated 3D structures with an inkjet printer, maybe using light to polymerize UV polymer, or just directly using something like wax, which you can heat up, jet, and set. And that has an advantage over conventional inkjet inks, because inkjet inks are a suspension of pigment particles in a liquid carrier, and that leads to all of your problems with inkjets getting blocked. And Epson printers are famous for getting blocked continuously because they have this separation of the inkjet cartridge from the inkjet print head, which means that the print heads are very high quality because the cartridges are only just a dumb bucket and all of the engineering is in the printer. But obviously it means that the print heads can fail. But if we're just printing liquid wax, it's no problem. There are no pigment particles. We can just heat up the wax and it's a liquid. So there's a little heater circuit that I made. This is a big power transistor, which is essentially just being used as a heater. Just short out the transistor and control the current, and you have a heater. And then just next to it is a temperature sensor and a little bit of control electronics to set the temperature. You can see that the heater part of it works. You can melt wax and it comes out of the holes, so that was easy. The next bit is to attach the printhead itself. So because the ports are very, very small, we needed a kind of gasket material to bridge the gap, and so we just used a laser cutter to cut out some little gaskets out of a double-sided sticky tape. And that's a kind of a really cheap, quick, hacky way of doing some kind of almost microfluidic assembly. So there's the printhead with the gaskets. And yes, that didn't actually work because it turns out that the double-sided tape fails very quickly with being on a heated inkjet plate. So then we tried a silicone sealant being deposited by stenciling it through a laser cut stencil, squeegee it over the stencil, and then you've got your precision silicone gasket. And that worked for a little while, but eventually it became leaky. And that's the main problem with this machine at the moment. It's just very leaky. So if you have any ideas for better sealing, do let me know. Finally, I landed upon some laser cut rubber gaskets and some mechanical compression to fit it all into place. And that just about worked. So reverse engineering the electrical interface. There's been a few attempts at this in the past for various Epson printers. Particularly the POSAM project is really cool. This was a DNA printer at I can't remember where, an American university. It turns out that the inkjet printers are a very well-used research tool. Lots of people use them, particularly in biotechnology. But usually they use these sort of research-grade machines that are maybe a few $100,000. And really they have almost identical capability to your €40 medium arch printer in terms of the droplet size and everything. But the only difference between the two platforms is that the laboratory platform is designed to be hackable. It's something that you can adjust the kind of drive waveforms to adjust how the printing cycles work. It's just exactly like the Epson printer, but you just have more access. So the question is, can we, by reverse engineering the Epson printer, create a laboratory-style hackable platform for less than a few $100,000? And yeah, spoiler, the answer is yes. So the first place to look when you're trying to reverse engineer a piece of consumer electronics is look at the patents. Reading them is exceptionally painful, and I wouldn't recommend doing that. But if you just look at the pictures, you can begin to get an idea of what's going on. This is the electrical interface between the printer and the printhead. It consists of two serial buses for the color and black data. I'm not entirely sure why they're separate. This is probably some sort of bodge as a result of gradually evolving the standards back and forth for different platforms. Also at the top, this is an analog waveform which is actually delivered to the Piezo membrane actuator that you saw in the first slide. So as the ramp goes up, that very much maps onto the physical motion of the diaphragm moving up to suck in the ink, and that moves up slowly, and then that rapid downward part of the curve is the droplet being ejected, and then there's the slow recovery for the diaphragm to move back up again. So just by controlling the shape of this analog waveform, we can control the motion of the printhead and potentially adapt to different kinds of inks that have different fluidic properties. And you can see that this patent is talking about having different parts of the printing cycle so that you can print actually different diameters of droplets and have different levels of grayscale, which is completely nuts. But for my thing, I was only interested in getting ink out of the printhead and nothing more. So here it is at a kind of schematic level. At the top, we have that analog waveform, and then that controller IC, which was the small brown object on the flexible circuit board. That's the thing we want to be able to control. It internally has control over some switches, and it essentially multiplexes that analog waveform onto the different droplet firing nozzles. And by setting up the image data over this serial bus, you connect, for example, the second, third, and fifth nozzle to the high voltage, and then when you give it that high voltage spike, out comes the ink in the image. And obviously that print data bus on the left is the thing we're trying to hack. So there are lots of really cheap open source hacking tools available. This is the OpenBench Logic Sniffer, which is a really, really cheap, I think it's about €30, quite high speed parallel bus sniffer. And I just attached that between the printer and the printheads. It's a bit of a mess, but you can see that there's the printer with the USB connection coming in from my laptop and the existing printer control board there. And then I've just intercepted the ribbon cable that leads to the printhead and attached that logic sniffer, which is in the middle there. And that's just capturing some traces. So these are the traces captured from the printhead, and I was very happy to see that they line up pretty closely with what's in the patent. So immediately I was able to figure out what the different signals were. And then I built my own piece of hardware to try and replicate those signals. This is basically a kind of flexible development platform for controlling the shape of the analog waveforms that are delivered to the droplet drivers, and also for just sort of adapting the parallel bus as necessary. So at the moment, this doesn't have any sort of USB interface or anything. It just takes a pre-flashed image, which you load onto it, and then it produces the correct drive signals. That's what my analog waveforms look like. I took some inspiration from the datasheet, but sorry, from the patent, and also from the waveforms that I recorded from the Epson printer. But I found that printing the wax was very different from printing the water-based ink. And so I had to bugger about with the shape of the waveform to actually get anything out of the printhead. But I did manage to eventually get some droplets out. And it's quite a flexible hacking platform. I've released all of the materials if you're interested in designing your own and hacking your own printer. But essentially it has, for the analog portion, a memory attached to a digital to analog converter and then a high voltage amplifier. And so you can actually, these waveforms are directly synthesized from memory. And you can actually just see on the slow parts of the trace the individual bits in the waveform step by step. So we could have really any shape waveform we like. And that makes it quite flexible for printing different materials. So this is the completed hacking platform. We've got my control interface there. Next to it is the temperature controller that's maintaining the printhead at 54 degrees. And then there's all the mechanics is just harvested from a couple of old printers and bodged back together again. Oh yeah, the hacking board also has a couple of stepper motor drivers as well, so it can do the motion control part as well. So results. This is a Lego brick and under the microscope. If we zoom in, you can see that we've inkjetted some lines of wax there onto a copper substrate. I was interested in using the wax as a resist for printing circuit boards, as well as for printing 3D wax objects. So I was printing a lot of wax onto copper to see how the material stuck together. This is my favorite photo. These are some tiny 3D structures made out of wax. So these are tiny droplets of wax stacked up. Each one is 1,000 drops high. And again, this is on top of a Lego brick. So you can see that the technology is capable of some pretty ridiculous 3D resolution. And this was after absolutely no optimization at all. But I was really lucky. As soon as I could get the waveform the right shape to get wax actually to come out of the thing, I just stuck a Lego brick under it, hit print, and this is what I came out with. So I was very happy, and I think there's a lot of potential for taking it quite a bit further. That's a close-up view of one of these things. They're pretty crazy. I was lucky enough to have access to an old university professor's friend's composite microscope setup. So this is a kind of composite image of lots and lots of photos at different focal depths, so you can really see the 3D structure of the thing quite nicely. Here it is printed out onto a piece of copper. I was trying to print a solid square here, but then when I etched it, I actually came out with almost the individual print parts. It was a bit messy, but so there's obviously quite high 2D resolution accessible as well for making circuit boards potentially. So I tried to print this out. This is my pre-flash data that goes into my controller. Unfortunately, this is the biggest image I can print at the moment due to my my lack of flash memory. I've only got a few 100K to play with, and it's implemented incredibly badly. But it's a proof of concept. You can see it printing there. It's come out in a small window. I'm not quite sure. Right, there you go. You can see the image coming out and the motion control happening. That's the image as it comes out. And this is on copper, so I tried to etch it and made a little circuit board out of copper wax resist. So this is trying to push the resolution down a little bit further. You can see the edge of a €1 coin there, and we've got some quite dense text. So I think it's definitely a promising rapid prototyping technology for printing circuit boards, and also I think for printing 3D wax objects. So yeah, this is what I'm going to do next when I get around to it. Hopefully, at the moment there's lots of problems with air bubbles getting into the system, mostly through my leaky printhead to reservoir interface, and then as soon as there are as soon as there are air bubbles in there, the whole thing just fails and you have to kind of pump it all back through. So I need a better way of priming the nozzles. Incidentally, your Epson printer does this as well. It has a little kind of vacuum cup, and when the nozzle, when it parks the carriage, so your page is here. Once it's finished printing, it moves the carriage over here, parks it, and then this little platform comes out and sucks with a little peristaltic pump, sucks all the ink through to try and clear it out of bubbles. So I need to implement something similar. And it's unbelievable that your printer does all of that for 40 euros. I just can't believe it. So yeah, this is from a commercial wax inkjetting machine that exists for rapid prototyping jewelry and dental castings. So this is a commercial technology, but the machines are obviously crazily expensive and also extremely slow. The machine that prints this thing out only has one inkjet nozzle. Thank you. Good idea. Because I'll print my. Objects, and I think this is a really powerful technique. This is an ancient tradition, lost wax casting, where usually someone will carve a wax object and then convert it into metal. And it has the advantage of being ridiculously high resolution, so the wax is really almost perfectly represented in metal at the end of the process. But unfortunately, it destroys the master. But when you combine it with 3D printing, you can print out wax masters in bulk and potentially make as many ridiculously high-resolution copies as you like. So I use this technique for jewelry casting, and I just included this so you can see the kind of rough process. So you start off with a wax master, set it up on a base, mix up some plaster, pour it on top, vacuum out the air bubbles, put it in a kiln to fire the sort of very weak plaster of Paris material into a very high temperature, very high impact ceramic, which also has some pores in it so that the air can escape when you pour the metal in. And then after a few hours in the kiln, the plaster of Paris has become this hard material. You then pour the liquid metal in the top, and I'm using a vacuum table here to pull the air out of the mold to allow the metal to pour in the top. And it's pretty amazing. The air actually just gets sort of pulled through the pores in the plaster. So this is a completely solid block of plaster. There are no air holes or anything, but there are. They're extremely small pores. So just by putting a vacuum table on the bottom and pulling a really hard vacuum, that's enough to pull the material in the top. I had many failed attempts like that. So I built a centrifuge to pump the wax in harder, pump the silver in harder, and I got some quite nice results at the end of it. And once you tidy it up a bit, you end up with a 3D object. So this wasn't 3D printed. This was crafted by hand, and making the wax master took a long time. I'm very excited about the possibility of doing it in CAD, printing out a master, and then converting it into metal. So that was hacking for better craft. The second half of my talk is about using craft for better hacking. So this is a project I did for a band, Muse. They wanted this pair of video display sunglasses to display the lyrics of the songs while they're on stage. Completely crazy. You can't see through them, but yeah, whatever. Pays the bills. So.
Do they often forget their own lyrics?
Yeah, well, it's been known, I think. So here I started off with SolidWorks to make a 3D image to sell the project to them, basically. But then there wasn't really time to actually have them CNC machined, and they couldn't really be 3D printed because they had to be very robust for touring and surviving the kind of rough conditions of a touring performance. So I just made everything literally by hand with saws and files and bits of plastic and really traditional craft techniques. So yeah, I printed out my CAD in 2D and stuck it on top of the bits of plastic and then cut them out with the saw. And I didn't take enough photos, but you can see that's the kind of starting point. You can laminate lots of layers of this material. This is called acetate, cellulose acetate plastic, and it's basically not used anymore for anything other than custom spectacle frames, because all plastic objects now are essentially injection molded or sometimes machined. But this stuff is really optimized for working with your hands. You can get, it behaves very, very nicely with sort of conventional woodworking tools, essentially. And it used to be very, very common for spectacle manufacturers to make their frames this way by hand. It has this nice property of being soluble in, or sort of partially soluble in acetone, so you can lay up many layers of the plastic and then bond them all together with acetone glue. And then after sort of sanding and cutting, you can get some quite nice 3D surfaces. I wanted to get that curved shape, so you can also thermoform this material. So I made a little wooden mold with the sort of 7-degree angle that I wanted, laid the bit of plastic on top, and just heated it up with a hairdryer, and it just sort of drapes beautifully over the plastic mold. So you don't need anything sophisticated, just some basic tools. Obviously, the two eyes need to be connected electrically, so there's this little tunnel that goes through there between the laminated layers and allows the signals to go through. So I went into a bit more, I took a few more photographs of making the temples, the side pieces of the glasses. So start off with a plastic object, print out the image from SolidWorks, and then just with my little saw, cut out the shape, file it to get the 3D contours, sand it wet to make a nice smooth surface. And then a bit of milling here just to attach the hinge pieces. Tool making is a really important step, and something that the hacking and craft worlds definitely share. Sometimes it's worth just making a little custom tool just for one job. And this was a little custom jig I made for manufacturing the little side pieces of the little hinge rivets. So this is a way of, basically it's just a jig for cutting lots of pieces of metal to the same length and then drilling 2 holes in very accurate position. And using that tool, I could make a few of these little silver pieces. I had to make many of them because I kept messing up the next part, which was soldering the little pins on the back to make a rivet. So those are the 4 rivets that rivet the glasses together. You can silver solder them, but then you have to remove the flux afterwards. So this is a weak acid solution to just dissolve off the flux, polish them up, and there you have some nice little rivets. And then riveted them in place. Another beautiful aspect of this plastic is that you can actually polish it chemically. So instead of having to go through finer and finer and finer grades of sandpaper and lots of elbow grease, you can just get it roughly to a sort of reasonable finish and then dunk it in acetone for a few minutes, and the surface will sort of partially dissolve away and leave you this perfect finish. It's absolutely terrifying, of course, because if you leave it there too long, you just end up with some sludge. So yeah, I did manage to dissolve one piece a little bit too far, and I was very sad about that. So that's another nice little feature of these glasses is that they receive the cues for playing the content. The content's pre-recorded on the glasses, but they have to be synchronized up to the show. So there's this RF link to the glasses, and the antenna is a little wire that's buried inside the plastic over the ear, and then comes out of the hinge. So it's all quite nicely packed away in there. That's what they look like from the back. I made these stainless steel plates, again, same way, print out the CAD data, cut it out with a saw. I used the laser engraver here to mark the backs of the glasses. So it's this real combination of the old and the new, using a simple saw to cut out the shape, but then I've got a little CO2 laser engraver that's useless for cutting out metal, but it's very nice for sort of marking surfaces accurately. I think I'm going to skip over some of this, but I wanted to make some plastic inserts to attach the metal to the plastic, and I wanted to knurl the surfaces to make them rough so that they could bed into the plastic thermally. And I don't have a tool that can work on such a small thing, so I made this little knurling tool out of a pair of cigarette lighters. So again, applying that kind of reuse mentality to what you've got around, you can really make some quite nice tools for doing some quite precise work. So tapping the little inserts and inserting them into the plastic. And these are very, very small fasteners. That's a 1mm screw into a little insert that's embedded in the plastic, and it's quite possible to make all of this stuff just with your hands and a little bit of practice. So over to the electronics inside the glasses. This is a STM32 Cortex M4 development platform, and I just wanted to mention it to you because I talked to a lot of the people coming from the more sort of informatics side of hacking, traditional software engineers and security guys. And when they come to the world of hardware, starting from maybe scratch, it's quite common for them to pick up the hacker maker tools that are around, like the Arduino platform and stuff like that. But I think now I really wouldn't go for the Arduino. I'd go for something much more powerful because there are some incredibly powerful embedded hardware platforms coming out that are easy to use from an electrical point of view, maybe less easy to use from a software point of view, but you guys are all, pro software people. So you really have access to some incredible tools. This is a €10 PCB that you can get from Farnell in Germany. And it's got a 168 meg Cortex M4 core, meg of RAM, and some really amazing peripherals. It's got something like 17 different timer modules that you can configure, analog inputs and outputs, and it's way more advanced than anything in the kind of Arduino maker movement scene. And yeah, surely people are moving across, but the software tools for driving these things are currently a bit of a pain, but you guys can handle it. I use Eagle for designing schematics. This is a good place to start because it's very easy to use, and most of the sort of commercial EDA tools are really, really expensive, but this one's free and it's got pretty good Linux support. It's not open source, unfortunately. There are KiCad and JITA, which are open source PCB editing tools, which are pretty decent, but I don't know, I still use Eagle for some reason. This is the PCB layout, so can you still hear me? Yeah, good. So PCB layout, you essentially take your topological view from your schematic editor. That was the white step. You can then export to the kind of topographical view, which is the physical connections in copper, and then you sort of lay out all the tracks, and you end up with the design like that. So this is 4 layers of copper, with most of the wiring on the inside and the outside, and then some power planes in the middle. And it's quite a dense design, but it's still fairly easy to do with these quite cheap and accessible tools. So once you've got your circuit, we didn't actually have time to get it assembled by a PCB assembly house, but fortunately it's quite easy to do it essentially in your garage. You can order the PCBs on some pretty rapid services. This one was actually a four-day turnaround to get the PCB from an email to a physical object in my hand. So there are really, really rapid PCB fabrication services available now. Also, if you want to, so that was very expensive to get a very high quality PCB in a very short period of time. If you want a very cheap prototype, you can go to China, and with about 2 weeks, you can get custom PCBs for ridiculously low prices, like €20 or something. But obviously, you have to ship stuff back and forth from China. So it's a bit of a pain, but very cheap. So this stuff's really easy to get access to. You can also order these stencils for applying the solder. So this came from a UK company. It has a one-day turnaround for £40. You email them some CAD data, and they'll ship you a laser cut stencil for applying your solder. Then you can just take your solder paste. Solder paste is a bit like caviar. It's tiny, tiny balls of solder in this kind of liquid flux goo. So it behaves much like toothpaste. You can kind of squeegee it onto your contacts, and then when you heat it up, the little balls of solder melt and then collude together and form your joints, and the flux kind of boils away. So this is an alternative to soldering by hand, and this is how production electronics is made in huge quantities. The solder is stenciled and the parts placed by robot. But actually placing the parts is pretty easy. So once you've stenciled your components, you end up with, hopefully, a little perfect tile of solder paste on each pad. And it's slightly sticky, so it's quite easy to just place your component on top, and it sort of sticks to the solder paste quite nicely. For about €30, you can get a toaster oven, to replace the several £1,000 industrial unit. And I actually profiled this with a thermocouple and plotted a graph, and it pretty much hits the JEDEC, which is an industrial body that regulate sort of standards for PCB assembly. It pretty much hits the time temperature profile curves. With a bit of practice, kind of jiggling the knob and opening the door at the right time, you can actually hit the specs pretty tight. So after that, they come out with all the components soldered in place. And just to give you an idea of time, this was 4 circuits with several hundred components on each one, and probably 40 or 50 different types of components on each one. And with a little bit of practice, you can get quite quick at placing them. I think I started assembling this project. I started squeegeeing the solder paste at 11 p.m. and by 4 a.m. I had 4 complete circuits. So it's a very, very fast way of producing very high quality output. Bringing the craft element back in, you can, if you don't have time to make multiple bits of development hardware, I actually made one PCB and then sort of cut bits apart and stuff to test it before integrating it into the glasses. This is cutting the glass to make the front panels of the glasses. These are some organic LED displays from China. AlibabaExpress.com is the way to go for incredible components, the kind of stuff that Samsung are putting into their mobile phones are available on Alibaba Express for pretty rapid shipping and pretty low volumes. So you've got to be prepared to do a bit of emailing back and forth and deal with a bit of Chinglish, but you end up with some pretty amazing access to parts if you're prepared to go through the pain. Yeah, this is the assembled device from the back, so it's quite a densely integrated product. And it's not far away from a piece of consumer electronics at this point. You've got a custom enclosure, which would normally be an injection molded part with tens of thousands of euros of tooling cost. I made that with my hands with probably a couple of days' work, and it ended up the same quality as you could have injection molded. So it really is possible to use some really simple craft techniques to make consumer level output, obviously only in prototype volume. But if you're doing a Kickstarter project or something and you want to impress somebody, it might not be worth sort of 3D printing something that's going to resemble but not completely emulate the final output. It might actually be possible with handcraft techniques to achieve the final output, just using a bit of elbow grease and a bit of patience. So that's why I'm advocating this sort of craft and hacking fusion together. You can actually produce some very high quality output. So that's the final product. Oh, there should be a video here. I'll show you a video later maybe. I also wanted to, since I'm at a security con, I wanted to somehow justify my presence here by starting some conversations about hackercraft and security implications. I mean, it obviously has implications in physical security, but there's a lot of FUD on the internet at the moment in the media about kind of the hazards of 3D printing and homemade guns, or this is one a bit closer to home. A German hacker, Ray, made these 3D printed keys at Hope, I think it was last year, and defeated some shitty handcuffs with them. So there's something happening in the physical security world, in the confluence of craft and hacking and certainly lockpicking, but I'm not exactly certain what it's going to end up as. So this is my workshop. I just wanted to mention that all of this stuff was essentially done in my flat. I'm a student at the moment, don't have a lot of disposable cash, so I've got a one workshop, one living room, everything space all together. So there's no excuse if you've got a bit of disposable income like you IT security professionals. You can dump a bit of it into tools, and it's a solid investment. So yeah, there are my contact details if you want any more information, and thanks very much.
Thank you very much, Jeff.
Yeah, I'm working on the
video.
I'm working on the video. I've got one here somewhere. What do we got here? Yeah, this one. Oh, do we have an audio connection here? I might be able to plug in a. Can I plug in my sound card? Is that possible? Yeah, thanks. Let's see what happens.
Maybe it's also hardware fuzzer, I don't know.
It's a possibility.
Yes, it looks like.
Move my laptop a bit so that we can plug it in. So I guess we can leave that playing and take some questions.
Okay, questions. Great. wait.
So Muse must have given you some disposable income, though.
It's true. Yeah, obviously it was a job for money, but not a huge amount of money.
Yeah. So the glasses, they display the lyrics on the outside, is it?
That's right, yeah. It's for the audience, and he has to stand there looking cool and dealing with the fact that he can't see anything.
Okay, more questions, or do you want to just watch the video?
We definitely need to deal with the vision problem.
Yeah, great.
I did actually look at building in some tiny periscopes into the glasses to see sort of out of a couple of lenses here. And it is possible, because if you look at your mobile phone, the lens for the camera is only about 2mm diameter. And it condenses probably a 60 or 80 degree view of the world down onto a tiny imaging chip. So I'm sure it's possible to send that image and then project it back into your eye from the inside. I don't know. I tried, I didn't get very far.
Okay, more questions? Yeah. Great.
I was wondering about power for the glasses.
Yeah.
Was that just a battery on the board?
Yeah, it is. It's, I'll show you the insides again.
Was there enough power to maybe mount some lasers on the glasses?
Absolutely. Absolutely. I mean, these lithium polymer batteries are pretty good these days. They've got pretty high capacity, but also for your lasers, you want really high discharge current. And the ones for remote controlled helicopters and planes are rated for tens and tens of amps of discharge current. Obviously not for very long, but yeah, I think high energy pulsed weaponry is totally feasible. You can see the battery in the bottom corner there. That's I think it's about a 300 milliamp hour battery, and there's a cutout in the PCB to fit it all into the thin form factor. It all ended up quite thin in the end. It's about 10.6 millimeters total thickness with all the electronics, battery, PCB, display, and a piece of scratch-resistant glass on the front as well with anti-reflective coating. So it's all quite thin, and it's definitely possible to achieve like consumer technology level of density just by hacking it.
Is that the RF21B radio?
Yeah, it is.
Okay. Where do I buy tickets for a Muse concert?
What about what, sorry?
Where do I buy tickets for a Muse concert?
Yeah, okay. It hasn't been through a thorough security audit, so yeah, you should definitely get down to any of their live gigs. Yeah, hack it.
Yeah.
So, Jeff, what are you going to do after the talk?
Yes, thanks, Florian. I'd almost forgotten to mention. So, I'm currently at design school, and I've got one project left before I graduate, and it's about society and surveillance and personal anti-surveillance tools for living in a dystopian future like the UK or the US. So just after this talk, I'm going to go upstairs to the speakers lounge, and I'd love to talk to a couple of you guys about surveillance in public. And particularly at the moment, I'm looking at Google Glass as a potential future scenario that's about a year away, and the public needs some response from the hacker community, I think. So possibly my project is about open source surveillance tools. At the moment there's a totally unequal distribution between the governments or the police forces or large corporations' access to surveillance technology and our access to surveillance technology. And perhaps if we accept that surveillance tech is out there, maybe we just need to open source it and use it ourselves to watch the watchers. That's a potential direction it could go. But yeah, as you can tell, I'm really a hardware guy, and I'm very new to certainly the InfoSec field, but also to the kind of political space. And I know lots of, particularly in Germany, there's a lot of political activism in sort of data freedom and surveillance and anti-surveillance. So yeah, if anyone's got any thoughts and would like to come and join me upstairs, we're going to have a little chat, and also it will be filmed so that we can upload it to the internet later. So I should warn you that up front. Yeah, thanks.
Okay, thank you very much, Jeff.